So, my name is Ivan Panchenko, and I will be talking about my experience in transforming data types. So in PostgreSQL, we have such an interesting thing as transforming or transform. What it's all about? As you know, in Postgres, we have certain procedures, different languages. The point is that when in a language interpretation unit, we have our own particularities, and so not all the language you use are transmitted ideally. For example, Perl, this is a procedural language where you can see quite a simple function that takes on certain parameters of quite popular types, and actually then dumps its contents in the way it was received at the very beginning. On the right hand side we can see how it is actually then forwarded. So we can see that int simple way was received in form of a text. The text received in the form in text byte was received in a quite bizarre form. As array, it was received in a similar way, looking just like array, but not quite a trivial one, JSON. That was just a text, and even more unpleasant bool type was also sent in form of text. And of course that is terrible, because from the Perl PL point of view, Perl, it's not just like false, but it's true just like any other empty line. So what we're supposed to do that? So we have it in Postgres, and where we can have two couples, different types of language, where we could use take data from the procedural language into Postgres, and then in the backward direction. Well, it is quite fast and simple, and after transform appeared, here we received then a special function for JSONB. So this function was written PL Perl and JSONB. They were packed in this transform, and then it was exposed to JSONB PL Perl extension. And after that, you don't have to worry about JSON, how it's actually forwarded, and that it should be manually parsed, etc. But it wasn't done for quite useful and simple type as bool. And when I saw that, I decided to create a contrib. So it was quite simple. Here is the function and the way they look like. So we received parameters from the function, and then give it back in this form. So on the left hand side we used bool Postgres SQL in PL Perl, true or false, and on the right hand side it's quite the opposite. We take PL Perl, we take it and then check it out whether it's true and false, and then receive it as a result. Well, it is absolutely simple. This is very, very simple, and there you can understand how to write all those transforms. It's very simple, as JSONs, they're really big, because JSONs are very simple, but it could work for this kind of simple types. Why I'm telling you that? Because you could also work on transform. Here is the result that we receive. Here is we have a new extension. It's already available in Postgres number 13. As for functions, here we have additional words, transform, and we specify type where it can be used. And on the very same data, we receive JSON in form of data structure, but not in the form of text. And then we receive their bool, and false is received like an empty line, and then we also receive true, which is regarded like true from the Perl point of view. Seems like this problem is tackled, and I would like to also work with other types. And those who are interested in extension programming, you could also find out more about Postgres content and write something like this, quite a similar thing. That probably it could also become a part of Postgres. But the typical standard task there is to work with new types or new functionality already exist and available. I mean, date and time that can be transformed in some kind of convenient things for procedural languages.
Then intervals, time intervals, interval times like ranges, and many other things that you may think of, like spatial types. And JSONB is really good with lazy transform that would not want to roll out the whole structure from you one view to another, but only something that you needed. So you're welcome, and work with us and code. My name is Mikhail Jilin, and I'm Postgres Pro employee, and I'll be talking today about index-only scans issue and how we managed to optimize this on big tables. So, what is index-only scan? This is a nice functionality that allows some queries to run much faster due to data being selected not from the tables themselves, but from indexes. It's really cool. And the key thing here is why you need these index-only scans you want to use. You would reduce the load on I/O. It's really helpful if it's really overloaded. But there are some minor drawbacks. Let's take a look at a simple case. There is some log table, and you have the message itself in there, and date column. And we want to check out the logs for 2 days, 1st and 2nd of February. Sorted, and only 100 records. So we have created an index following logs with these 2 columns. So now we're taking some test table with 1 million lines. It's great plan, index-only scan, and we have used we read only 5 buffers, and all of them are in cache, which is good. So it's so nice. And then we go to production or some test environment, and we see that it's not 1 million lines, but 20 million lines. And somehow hits is increasing a bit. Oh, not a bit, like it's 20 times larger. But why is this happening? Well, the table is bigger, that's true, but it shouldn't have led to significant increase of buffers that we read. So what's the cause? The problem here is with the way this functionality works. It iterates over rows that it took from indexes, and it checks whether the row is accessible to read or it's invisible. Maybe it's some new tuple or some removed tuple, and it uses visibility map for that. And the index-only scan functionality itself, it takes and caches only single visibility map page. And I want to remind you that a VM page takes up 256 megabytes of table. And if the table size exceeds 256 megabytes, then we start jumping between these pages when we are iterating over rows. So one time it's one page, and next time maybe we'll get into a different visibility map page. And this jump does not come for free. First, we have to clean or unpin the previous buffer. We need to find the new buffer, and then we have to pin it back. We need to cache it. And we can see that unpin and pin operations are exclusive, and we cannot do pin and unpin on the same buffer in parallel. What does that mean? It means that if we add some load, namely if we take some powerful machine, 4 processors, 80 cores, physical ones, we take huge buffers to avoid any disk I/O, then we can create this kind of graph depending its dependence of rows per second and processes. And the first case is 256 megabytes table, and the other one is 2 gigabytes. And suddenly, if there's only one visibility map page, then performance is improving. And when it's 2 gigabytes, it does not happen like that. Why? Because severe blockages start in these buffers. Because we turn our Postgres to a single flow thing. Well, not single flow thing, but something like that. So naturally, we need to optimize. How about we cache not only one page, but a bunch of VM pages? And as we see in the yellow columns, our performance grew considerably when you have, if you have a lot of visibility maps in the table. Then we increase the amount of shared buffer partitions to make sure that we are really good. So the conclusion: index-only scan drops in performance when table exceeds 256 megabytes, but there is a patch, and it's already prepared, that improves scalability by many times. And actually, it improves latency when we have some big scanning processes. It's been checked by testers. Patch will be sent soon to hackers by our developers. And thank you very much. I want to renew this sprint tradition. Oh, we had only one in 2006 in Toronto. We have got together and we were hacking Postgres. So this is a real image, and there are quite a few famous people sitting here. Unfortunately, you can't see the most friend of yours because he was sitting next to me when I was taking a picture. So after the presentation in the smoking room, a guy approached me, Alexander, I don't remember his last name, and he said that there is a big problem because it's really expensive to stream by IT. So that inspired us to try and fix it, especially since it's a bit connected a little bit to what we work on with JSON-B, and we have created this example that motivated us. 100 megabyte table, well, a table with a single byte uncompressed. It's just letter A. And we add 1 byte. And it takes more than 1 second. And this example really motivated us, especially since table size increased, 100 megabytes of wall on top of the table being 2 times larger. So that's really not nice. So what did we do? We thought that, okay, we need to fix toast because current toast is not really good for partial update because all the data are detoasted before getting modified in memory. That when we added 1.5 kilobytes, we saw that 4 new toast chunks appeared. Of course, that's not efficient, and we want to do it for it to work differently. So, for instance, if we added 1.5 bytes, that fits in line. The old chunks, they're shared, so new ones are not appearing. We want it to be like that, so some link or reference appearing. And in the record itself, we are keeping this new small bit that is added. And if it's more than 2 kilobytes, then we keep the first 2 chunks, we store them, and the third is modified, which leads to new chunk appearing. So this way, instead of 4 new chunks, we get 2 new chunks. So running the same example again, we sped by 2,750 times. 2,750 times faster. I really like such examples. So we can predict even the maximum win. And the size of the table didn't change. And it was only 143 bytes added to wall. So there were no extra buffers read or written. I think it's a really good example, and we have came up with a more detailed example. We took a table with 100 records of different lengths, and we appended it from 10 bytes to 1 megabyte. So on the left-hand side, we have master, we see the query time is proportional to the length of the old record and the new record. See, we have toasting started and it started growing. So these flat sections we have here, because it's 10 kilobytes are added, it's more than 1 kilobyte. So that's why what determines the extra that is added. And with our patch, we can see that time here depends only on the size of the added tiny piece, respectively of the length of the tuple itself. And we took the maximum length of 1 megabyte. So here it's only 1,000 times faster. If we take a look at the wall traffic, we see a similar picture. Master is really bad, and that explains what Alexander saw in his examples. And our patch led to the following: the traffic and big additions depend on logging. And there is some artifact here. There is wall growth here to the size of tuple 2 kilobytes. It is explained that we weren't perfect because we are logging old inline tuple piece. Well, we should log it, and then everything is going to be fine. It's because we had just some very little time, some night time. So we saw that everything's doable. And we have demonstrated considerable performance improvement, like 1,000 times improvement, and you can play with it. There's a link here, slides are here. It was a quick hack, but it opened the whole vista of opportunities, adding it to our work with JSON-B. I don't think that we have to optimize insert delete, but prepend, truncate, it's okay. It's also about data performance. But I think the main thing here is that we need to make sure that toast is pluggable for data type to know how to toast it better. Here, we have our contact details. If you want to work with our team, please contact us. And this example just showed how important your cases are for us. Basically, 5-minute long conversation with a guy motivated us to an interesting new development that gave us so much. So please share your pains with us, your pains with Toast, and it'll help us create new things, how to work with Toast. Thank you very much. Let's talk about fixing transaction. So let's meet each other first. My name is Vladimir Sitnikov, work in Netcracker, and one of my favorite things to do is committing BG JDBC. It's a driver for Postgres. Commit. There is so much to this word, right? And how commit command may fail. Well, it doesn't fail. It's reliable. Postgres is a reliable database, and all the days of conference proved it. But still, there might be an error. There might be an error, but commit should commit the transaction, and which command if not to commit? Well, probably depends on the case, right? So let's take a look at the easiest option. We connect to the base, create transaction, remove some sequence, it does not get deleted, and we launch the next query. And I'm sure that everyone saw something like that. And after that, you cannot fix anything. because database says that, come on, your transaction contains an error, you can't run it, and any query will fail. How to complete it? Well, you have to fix this transaction, say commit, and this transaction ended unsuccessfully, for instance. So we somehow need to commit it. Nothing new here. I'm sure people are saying that, yeah, defer constraint. Indeed, if you create a table where you have constraint that deferred manually, so we will insert similar lines, and what will happen? It'll fail when we'll try to commit transaction with an error code, but you cannot do it. Look, so commit may fail. So there is nothing new in it, right? Yeah, but let's think about 2020. Well, not the 2020 we are all thinking about now, but still. 1 year ago, an email was received vicious by hackers, and they say, yeah, come on, there is a standard describing what should happen if commit fails. Well, yeah, everything fails, so. But the guy who wrote it, he or she considered the case when commit does not commit. Same beginning, we launch the transaction, and then we enter some totally incorrect scale phrase. What happens? Drum roll, we say commit. And this is rollback. But rollback, well, but we were asking for commit, and no criminality, there's commit. But actually, if there is an error, we need to work on it. But it depends on the case. Now everyone started running around saying, "Oh, what do? We cannot roll back." And what PGJ DBC does, driver repeats the database behavior, and it doesn't try to create some other database out of Postgres. That's why we are trying to do the same thing, but user did not expect it. So we said, how about we create this patch that would recognize those rollbacks, saying that this is an error. We commit, we got the results, and the users
like. Yes, we have a mistake, but applications were not ready for such mistakes, that they were already there and that they are already there in the operation. So what would I suggest for you? The first thing is just let's have a look and to just see, don't you have some rollback of transaction? For example, you fix transaction data is rollback, then you don't know about that. So let's write a patch in Postgres. You must say, okay, we can write a patch, but then it turns out that in commit operation there is a certain continuation, for example, commit and chain. And if you knew that, then great work. But actually, this commit and chain operation is something that commits and creates a new transaction right upon completion, after completion. And again, whether it's successful or not, and what actually this mistake will mean, we'll see whether a new one